Okay, so here's the inside of the upper part of the arm of the PUMA 200. You can see 3 different motors for the 3 different axes. I'm not exactly sure how they connect, but we do have the mechanical drawings. And then you see over here, these are the air switches, solenoids for air, because you run your air into here. Then you can see they run the tubing all the way through. And then this is the pneumatic tubing that comes out over here and then goes into each side of the gripper. One makes it pop apart, the other one makes it grip, and you can control how tight it grips by controlling the amount of air pressure you deliver. And then you can see in here, in this other one, because it's not hidden, that bearing, that roller bearing that they have there for this part of the arm. And this one you can see is broken. It looks like the encoder broke. This is our part spot, but gives you a good chance to kind of see how they crammed so much stuff. These actually pivot, these connectors here. They allow the angle to change, kind of like a U-joint, not exactly sure. Then you can see the bearing, the gear that they have down in there. And then there's 2 more motors up here. One of them controls this rotation, and then the other one controls this rotation, and then there's this final motor controls this turret here that pivots the whole bot like this. So there's 1, 2, 3, 4, 5, 6 motors for 6 axes plus the pneumatics. And for some reason, to do all that, you need that many pins, and it's because these have encoders on each of the motors that have their own separate feeds going down to that. And then obviously the control for this, and then each of the motors needs to be able to run both directions. You can see the upper part, that drive shaft goes down to this joint here, which spins this part, and this drive shaft couples to a gear there that controls the pivot going up and down. And what's remarkable, really, because this is a first generation, this is the first electric robot that was ever manufactured. The PUMA 200 and the PUMA 500 came out at the same time. And how many of the problems they had already worked out, and how much, without the aid of CAD, how much quality engineering goes into something like this that has such a high level of precision. But with relatively crude encoders, just DC motors and crude encoders. And the motors just, it looks like it couples down into there. Oh, there's a gear on the side there. A hole where the gear goes in. And I'm sure there's a corresponding one over. Oh, that one actually has a direct drive shaft going straight to the center of the gear that rotates this joint, and then it pivots this way, and then this end bit also rotates. So those are all the different degrees of freedom for this assembly, and then there's 3 more on the other part. Okay, so we're making a quick video about what these Unimation controllers for the robots were all about and what was involved. Modern robot controllers don't take up anywhere near this amount of space. So our goal with this video is to try to understand what's taking up the space back then and how do they do it better now.
First thing that takes up a lot of space that doesn't anymore is the power supply. So these controllers use a really large power supply. This is a linear power supply, which basically means that it's very inefficient compared to modern power supplies, which can be much smaller and much more efficient. Basically, how a linear power supply works is it takes in the 60 hertz AC, runs it through a transformer here to step it down to maybe like 60 volts AC, and then it puts it into these big capacitors here, which smooth it into DC, and then it may run it through a final step where it regulates the voltage down to like 50 volts, 40 volts, something like that. But in a modern power supply, they're able to, instead of using 60 hertz AC, they actually convert 60 hertz AC into DC and then switch that at many kilohertz or even a megahertz, and then run that through a transformer and capacitors. And because the frequency is much higher, much smaller transformers and capacitors can be used, which improves space and also efficiency.
And do we know what this board is?
Yeah.
It says made in Ireland.
It does. Yeah, so the next thing that takes up a lot of space is the motor driver boards here, or I think they call them the amplifier boards. So, the motors in the robot need a lot of power to run, or the way they're doing it, they're using these big power transistors as basically like valves to allow power or not, and they kind of vary how open the valve is to control how fast the motor moves. This works really well, but it takes up a huge amount of space and generates a ton of heat. So in modern systems,
Is that why we have this big fan here?
Yeah. Yeah, you've got this big fan to cool it. If you look through the side, you can see these giant heat sinks, and it's just a chain of big power transistors all the way through.
Actually, go grab one of the other ones, and we can look at it from the other side.
Yeah, you can see this is the same board, but taken out. And it's got this giant row of these big power transistors here. And these are basically like valves that open and close varying amounts to provide power to the motors. So the more open the valve is, the faster the motor runs. But it's like a two-way valve. You control either power going to the motor or the power getting turned into heat. And so these are very inefficient. In modern systems, they use switches instead of valves where they're either on or off. So they don't produce nearly as much heat. And then they just switch them really fast. So, if you switch it so it's on 50% of the time, off 50% of the time, and you do that thousands, like 10,000 times a second, that's basically the same as one of these valves being 50% open. That technology wasn't mature by when they made these. Finally, back here we have the computer and controls section. So each one of these controllers actually has an LSI 11 computer in it, which is a early digital computer from DEC, Digital Equipment Corporation. They were a big like mainframes, mini computers manufacturer. And so the actual computer part is this card and this card, like these four cards here are the actual computer part. And this computer runs Val2, which is their own programming language and operating system, which Unimation created in order to control these things. And then here we have the servo boards. So the computer provides information and says, I want this motor to go here, I want this motor to go here, I want this motor to go here. And these boards are responsible for actually making it happen. So each one of these boards has a digital analog converter, like a 12-bit digital analog converter to control how fast the motor moves, and then a whole processor on it in order to read the position of the motors from the robot and then control the motor's power in order to get the robot to move in the desired way. And then it also sends data back to the computer, letting it know if there's a problem. And this one here, this is an EEPROM memory. And so this is what stores the program for the microcontroller on it. And these are erased by exposing them to UV light. That's why they have this little window. But as you can see, the protective cover on this one fell off. So it's presumably blank now. So we'll have to figure out how to reprogram that at some point.
Do we know what these cards are?
These are, to the best of my knowledge, interface cards. So this one provides like the power and everything for the computer, and a bunch of the encoder signals from the robot come through this card into this backplane, which is basically a giant connector that connects all the cards together. And then this one is the card that actually forwards the output of the servos, or of the servo controller cards, to the power amplifier boards.
Okay, and then this is the back of the big connector that goes to the robot.
Yeah, this is the big connector that goes to the robot, and then here, this big circuit board with all the connectors on it is for all of these connectors, which are external I/O, so like external sensor inputs and stuff for the robot.